Okay, so I think we can start. So today we are going to do so today we are going to actually prove this Weyl integration formula. So the theorem is the following. So this setting is let F from Hn to C be a smooth unitary invariant function. Unitary invariant. Say smooth function. Then you want to integrate this function of h with respect to the Gaussian measure, with respect to GE over HM. You can write this, you can reduce it to an integration over the n-dimensional Euclidean space with Gaussian measure K. So this is equal to Cn integral over R capital N f of lambda product of lambda I minus lambda J squared, I less than J less than equal to lambda 1, d mu lambda 1, d mu lambda n. So this is the formula. Let me explain the ingredients. Left-hand side is very clear. Of course, d mu of h is, by definition, exponential of minus 1/2 raised of h2, the Lebesgue measure. Right? It's a weighted Lebesgue measure, weighted by Gaussian, dv of h. Cn is a constant that depends only on n, nothing else. Cn is a constant. Now here lambda is a diagonal matrix, lambda 1, lambda 2, lambda n. Lambda is a diagonal matrix, lambda 1, lambda 2, lambda n. So you can think of lambda also as a vector in Rn. And we are calculating the function over only on the diagonal part. This is, of course, I will explain what it is, this middle term. And these are Gaussian measures. We normalized the Gaussian measure. So the lambda is equal to 1 over root 2 pi integral over r exponential of minus 1/2 lambda squared. Oh, what am I doing? It's no integration. Just this one, Gaussian, and then low integration. So this is like a one-dimensional version of the thing on the left-hand side of d mu h. This is d mu lambda. It's a one-dimensional version. Okay. So this is a remarkable formula because we'll see gradually why this is remarkable. But at the surface of it, you see that this integration is over space of dimension n squared. Now is reduced over space of dimension n. At the cost of introducing this weight, the weight, of course, you identify what it is. Product of lambda I minus lambda j squared, I less than j, is of course nothing but the square of the Vanderbilt determinant, right? So this is equal to 1, and then we can put lambda 1, lambda 2, lambda n, and then lambda 1 n minus 1, lambda 2 n minus 1, lambda minus squared. So this is a square of the Vanderbilt determinant. As you know from linear algebra, this determinant can be computed explicitly and is equal to this product and squared. So, so this is Vanderbilt. Determinant. Okay. We can say a little more about Cn. Actually, we'll prove that Cn is related to some interesting quantity. It is a constant, but is really volume of the unitary group over some fixed number, which is constant number, n squared plus n. Yeah. Over 2. Yeah, times n factorial. Now, the volume of UN, you ask with respect to what measure? Well, we're going to put a volume form on UN, on the unitary group. Of course, it's going to be invariant, so it's a multiple of the R measure. But which multiple really will be fixed by putting UN inside this bigger space. So we get that. We'll get to that soon. But for now, this is the expression, more explicit formula for Cn, the volume of the unitary groups. Okay, so how we are going to prove this, I explained a little bit the idea behind the proof in the last lecture, but now let me just start the proof more formally. So first of all, if you look at this space, okay, Zwankin uses notations Zn, which is, I use notations n by n matrices. So this has dimension, so Z, we can use coordinates Zij. The Zij is equal to Xij plus I Yij. So it has 2n squared coordinates. It's a dimension of this guy over R is 2n squared. As a ring vector space is 2n squared. And of course, this Hn is inside Zn. And UN, the unitary group, also is inside Zn. So I need some basic information from differential geometry of volume forms. So let me write it here. Maybe we call some differential geometry. So imagine you have an oriented Riemannian manifold of some dimension and G oriented Riemannian manifold. Then this metric, this is the Riemannian metric. This metric G gives us an N form, which I denote by d volume of G, the volume form. So this belongs to a space of N forms over M, and N is dimension of M. How this N form, volume form is defined, it's an over zero N form. I mean, if you choose local coordinates, any oriented local coordinate chart, say y1, y2, yn. I can write an expression of this volume form in that coordinate, the volume of G in that coordinate system only is given by square root of determinant of Gij, right? Determinant of Gij, d by 1, which d by n. Now, this Gij is the matrix, is the Riemannian metric expressed in this coordinate Yij. So Gij is equal to the d by I d by j. Is the inner product of these basic frames defined by the coordinate system. Okay. So, of course, if you don't put this factor, this by itself is not a well-defined quantity because it completely destroyed it. You change coordinate, this will go into something else. But when you put this in front, something magical happens. This is independent of choice of coordinates as an M form. So, yeah, this is great. One more thing I need, which is very crucial in the proof, is the idea that so now imagine you have a map F from manifold to another manifold. So imagine you have a diffeomorphism. Diffeom means that it's one onto smooth with smooth fingers. And imagine you want to pull back this volume form here to a form over there. So you want to pull back the volume of G of N. So you have a metric here, I call it Gn, and I have a metric here, I call it Gn. And I want to pull back this volume form. Everything is very functorial or covariant in this case. This is equal to D of no, so this is equal to volume of F star of, or D volume of, yes. That's equal to D volume of F star of Gn. So to pull back the volume form by this diffeomorphism, it's enough to pull back the metric and then compute the volume form of that metric. This is a very useful fact. It's just that this formalism of differential geometry is covariant. It's very nicely set up. Okay. So another thing I need is, again, just very general thing. So we put a Euclidean metric on Zn. The metric was that the inner product Z prime is equal to trace of Z prime star. So we just take the conjugate, the Hermitian conjugate of this matrix, multiply and take trace. This is a positive definite metric. Good. This positive definite. So it's a Riemannian metric on Zn. And I want to compute its volume 4. So to do that, we just notice that, so what is the analog of this guy? So here, in terms of vectors, this is in terms of covectors. These are covectors, these are vectors. So the notation is the same. But this is Z, and Z, the inner product of Z in itself, is equal to trace of Z star. And this, in terms of coordinate xij, yij, this becomes sum xij squared plus yij squared I from 1 to n. You see, this is Euclidean metric. It's completely flat, this metric. And the volume form as a result is very simple. To compute the volume form, we just multiply all this. So far we just got that the volume form on this Zn is a product of dx ij over all I and j, and then product of dy ij over all I and j. Just a flat coordinate, and then you just multiply that. It's like d by 1, d by 2, d by n, and there's no determinant contribution because determinant is 1. Right? Because of that thing at the end. So this is a 2n squared form, obviously on Zn. Okay. But now we want to restrict this metric to the subspace Hn. See what happens. So Hn, first of all, is a subspace of Zn. So this gives us, this inclusion gives us induced metric on Hn. So in this case, then HH is equal to trace of H squared. So I'll just follow the same rule that we have for the inner product. We compute the length. We get trace of H squared. Now this we get something a little bit different. So we get sum xii squared. These are diagonal elements here. Plus twice some xij squared plus yij squared. I less than j. Because when we are on Hermitian matrices, only these coordinates are relevant. The other ones dependent on this. We don't have 2n squared, they have only n squared. So this 2 comes up. So this means that this guys actually is an orthogonal basis, but is not orthonormal basis because 2 appears. So when we go to compute the dual, the determinant thing, we get something different now. So we get this volume 4. So So again, this is induced volume form on this n is dv tilde of h turns out to be product of I from 1 to, and these are orthogonal still. So here nothing changes. So it's dxii. And then we have product I less than j root 2 dxi in j, and then times root 2 d by j. Yeah. This root 2 because of this 2, and it has to be 1 over 2 because we are dualizing. Okay. So, I mean, this we have to compare it with the original volume form I defined. dvh was exactly equal to this, but without root 2. So I call this the induced, so it's without root 2. So this will change everything by a factor of 2 to the power n squared minus 2. Changes the Gaussian integral. Because this we have a choice of computing this integral over hn exponential of minus 1/2 raised of h2 dvh. We computed this and we got a factor of 2 to the power n squared minus n over 2. You remember we used the formula. So this is equal to 2 to the power n squared minus n over 2. And then there was this factor of 1 over root 2 pi to some factor, which I forgot now, but now if we use this, but if we tilde, this factor will drop because of these terms that we have here. So there's a little bit of nuance here, but that's that's okay. We'll notice that. Okay. Okay. So that's almost all of the preparation I need. But I need one more item, which is kind of interesting anyhow, independently as well. And that's the following fact. I mean, notation, actually. So if we erase these things. So more notation now. So this is something I can call it matrix calculus. So what's the idea? The idea is that imagine you have a matrix of functions. So this, so we have an n by n matrix of functions. Each of these guys is a function on a manifold. For example, by j goes from manifold m to c. For example, imagine they are real valued functions, or complex valued. Doesn't matter. Okay, so we have a matrix function. Now we can define its differential dA. By definition, is the differential of each entry. So it's going to be d fij. So this is a matrix of one forms now, right? On n. So it's a matrix of one forms on A, on M, sorry. I mean, by the same token, you can consider matrix of two forms on M and so on. Then it's not a problem. But there are two things that we need. One is like this rule. There is an extension of this extension of Leibniz rule. Is that D of A dot B, I mean, this dot, it's not a good idea, actually. You'll be confused with dot product. This is matrix product. I mean, it's clear. If you have two such matrices, you can multiply that, then you get a function, matrix of functions again, right? And the question is, what is the differential, according to my definition, of this product matrix? Well, this is equal to dA dot B, yeah, plus A dot D. I mean, clearly this follows from a usual Leibniz rule for functions calculus. The second one is also interesting, it's more interesting. So imagine your matrix is invertible for each x. So you can take its inverse, then you get the new matrix, which is the inverse matrix. And now imagine you want to take D of A inverse, which can be defined. But this, there's a very nice formula for that. This is minus A inverse, then dA, A inverse. Right? So how to prove this? That's very easy. So I just give the proof of two. How to prove this? Well, we have the identity A times A inverse equal to 1, right? It's the identity matrix. I just differentiate on both sides. P of A inverse is equal to, well, this is a constant matrix, which is 0. This is 0. And then I use 1, just say this is equal to dA times A, times A inverse, sorry, plus A times D of A inverse is equal to 0. And then I just multiply by A inverse to get D of A inverse is equal to A inverse, dA, A inverse, but with a minus sign. A inverse, dA, A inverse. Of course, this is a generalization of a famous rule from calculus that D of 1 over x is equal to negative dx over x squared. This is what we teach to our calculus students, D of 1 over x. This is quotient rule, right? It's negative dx over x squared. I mean, I put D because these are for me one forms. They are not functions. So, I mean, this is. But in the non-commutative case, we cannot bring this to the left-hand side. You see, if I could bring this to the left-hand side, it would be exactly like this, but that's forbidden. These things don't commute. But this holds. Okay. So, we think now I have only prepared for the material limitations fixed. Okay. All right, yes. Now, what is the idea of the proof? Let's go back now to the proof. So idea of proof. This is what we discussed on Monday. So we have this map, the diffeomorphism phi from Dn cross un bar to HNO. So Dn is the Weyl chamber, which is the set of all lambda 1 less than lambda 2 less than lambda n. Lambda I belonging to R. It's just a quadrant. There's a cone in the Euclidean n-dimensional space. Dn un bar is the left coset space, which is un over Tn, means the left coset space. Right. I mean, this Tn is the maximal torus, e to the I, take of 1, e to the I, theta n. It is a maximal torus. Okay. So we have that. And Hn circle, you remember this was Hermitian matrices with non-degenerate eigenvalues, distinct eigenvalues. So this is subset of Hn, distinct eigenvalues. And I proved that actually that this is an open, dense, full measure subset. An open, dense, full measure. That's it. This diffeomorphism phi that you can prove is a diffeomorphism, as I mentioned, using a spectral theorem easily. So what is this phi? Now phi, so I denote that something here by matrix lambda and some element here by class of some unitary matrix U. This is U lambda Usla. And this is independent of choice of representative in the class. You can prove that easily. Okay, so this is a diffeomorphism. And the idea of proof is that, so I want to compute this integral, right? So I know that this integral is exactly the same as the integral of this function if you restrict it to this guy, Hn zero, because this is a full measure subset. It's almost everything except on this zero-dimensional measure zero, I should say, subspaces that are not. So I restrict to that, and then I pull back this function with phi. I get a function over here, and I integrate over here. But then the price I have to pay is to multiply by Jacobian change of value. So I'm going to erase this now, actually. So the idea now is the following. Okay, so we have got this f here. So come to C. So if we compose, so this is f composed with phi. So this is the famous Jacobi's change of variable formula. Change of value formula tells me that this integral over there, f of h, d mu h over hn is equal to actually integral of f composed with phi times Jacobian of phi. I just write it like this. Jacobian of phi. Here there is a measure here which I have to tell you what it is, but so over the n plus un bar. Now this, so it's a matter of notation now. So what do I mean by this? Instead of using this awkward thing, I'm going to put the following. I'm going to put phi star of this guy, pullback of this volume, d mu of h. This is the invariant form of, so I don't put Jacobian, which is all the style. I put a fullback of this differential form, d mu of h. Okay. Yeah. Phi star of d mu of h. So this is now perfect. So the whole game now is to show that actually, is to show that this guy is exactly product of lambda I minus lambda j squared d of these guys times the volume for on this guy on un bar. F composed with phi is a very simple function. It's just here because f is unitary invariant. So when I compose it here, it won't have any u component. The u component goes away. It just depends on eigenvalues. A unitary invariant function just depends on eigenvalues because you can always go back to coordinates where that is diagonal. So it just depends on eigenvalues. That's all. So this is exactly that function f of lambda. This is clear. The whole thing is to compute this pullback or to compute the determinant of the differential. So, yeah. Okay. So we have to compute the differential of this map. Let me see if there are any questions in the chat. No. Okay, so compute. So next, compute d phi, the differential of E. Okay, for this, we can do now the following. Okay, so now the map is here. So phi of lambda and u, where lambda is a diagonal matrix, u is a point in the unitary group. So this phi obviously is defined not just on un bar, actually it's defined on un, because if I have a unitary matrix, I can multiply. I can conjugate it and then. So I just do that. So let's see what I get. This is equal to yeah. So I just write it like this: u inverse lambda u. So now so here's what is d phi? D phi is equal to d of. So we're thinking of these things now as matrix functions. So we use this calculus of matrix value functions. So this is equal to d of u inverse lambda u. So I just use Leibniz. This is d u inverse times lambda u plus, there are three terms, obviously. U inverse d lambda times u plus u inverse lambda d. Then I multiply this by u inverse u. So let me write it like this. So you do a little bit of gymnastics. This is u inverse u times du inverse times base u. This I don't change. U inverse d lambda u, and then the exterior term, the last term, I multiply also times u inverse u. Okay, this is identity, so I haven't done anything. So just do this trick. Now, this can be written in a nice form. Yeah. So we can factor u inverse on the left and u on the right. U inverse. Then I've got negative omega u plus d lambda plus lambda omega times u. So this we can write it as u inverse times L times u, where omega is, by definition, this one form, the u inverse. So this is a matrix valued one form. This is a matrix one form. This is a very famous one form that exists on any D group that's called Morer-Cartan form. This is the Morer-Cartan. One form. This plays a big role also in Chern-Simon theory, in characteristic classes, and all this stuff. This Morer-Cartan is a kind of God-given one form, except that it's not real value, it's matrix valued one form. And it's actually technically it's a Lie algebra valued one form defined for any Lie. It's called Morer-Cartan one form. And it's like magical. This is like almost like dz over z in complex analysis. It's a cocycle, and it's very important cocycle, but that's okay. Okay, so yeah, and L of course is like a curvature for negative omega lambda plus d lambda. I mean, this is almost like a curvature form. Yeah. So here we use the fact that to write it in this form, to write it in this form, use the fact, which is again very easy, that Morer-Cartan you can write it in a different form. U du inverse, u times the u inverse is the negative of the Morer-Cartan. Okay, so we can write this omega as omega ij, because these are matrix of one forms. And the fact that u is unitary implies that this is a skew symmetry. I mean, yeah, you need to realize that this will make this. Excuse me. Okay. So now we can write the entries of this omega. This is going to play a big role for us, this omega. So entries of omega are, or entries of L actually. So let me write it here. So entries of L. They are given by LII. I mean, it's a matrix of one forms also, but this LII is d lambda I. You see, there cannot be any contribution from the first two terms in the diagonal because they cancel each other. It's a commutator. First two terms is the commutator, so they don't give any contributions. But this gives us d lambda I for the diagonal because lambda is a diagonal matrix. So that stays there, d lambda I. And off diagonal terms, so this is diagonal. And then off diagonal. Yeah, so the off diagonal is Lij is equal to lambda I minus lambda j. That also quickly follows from this expression as the commutator. So, as I said, we have to compute the pullback of the Riemannian metric. To compute the pullback of Riemannian metric on. So we have a Riemannian metric here, which is induced from the biggest space I discussed. I mean, so, well, I mean, this is honestly inside Hn, which is an open dense subset in Hn, and this is a much smaller subspace of Zn, right? So there was a Riemannian metric here, it induces a metric here, and this is an open subset, you get a metric here as well. To compute the pullback of this, we compute trace of L squared because the map is so we have to compute the inner product of this function with itself, the differential with itself, right? But the inner product is given by trace because the metric coming from trace, and trace of this squared is exactly trace of L squared. So I should have to compute trace of L squared. That's it. So trace of L squared is equal to sum or ij from 1 to n, Lij, Lji. You see, these are differential forms. So if you're computing a new differential form here, this one. So this is equal to sum d lambda I squared I from 112. It's not a differential form. It's really of the type of metric. So it's actually skew. It's a symmetric form. It's not a skew symmetric. So yeah, plus some, I believe, I less than j. Well, actually, first of all, ij from 1 to n, L lambda I minus lambda j times lambda j minus lambda I j minus omega ij omega I. And this you can see is some e lambda I squared plus twice some I less than j dxij squared, because we can write this one form in terms of dxi and dij, dxij squared plus d squared. Yeah, so this is, I call this star, this identity. Okay. So now we have to, as I said, compute this pullback, which is now ready to be done. So let's compute the pullback of the volume form. So which is volume form of the pullback metric, but pullback metric is here. So we've got phi star of exponential of minus 1/2 rates of h squared d tilde, the adjusted volume form, not the original one. Well, this is equal to, I mean, it's given by that product of lambda I minus lambda j squared I less than j less than given 1. Product of v lambda I from 1 to n. Then we'll go across. Yeah. Cross product minus j towards the xij the yeah. And this, okay, so this d lambda I, because we are pulling back this guy, so it's going to be Gaussian on the real line. So this d lambda I is going to be equal to 1 over root 2 pi exponential of minus 1/2 lambda I squared. I mean, so this stuff should be d mu lambda I. Sorry, it should be actually it's d mu lambda. Yeah, this is d mu lambda. It's not d lambda. Yeah, sorry. I mean, d lambda is the Lebesgue measure, but this is the Gaussian measure. The mu lambda I. D lambda. Okay. I mean, that's it. So this proves this identity that we want, basically. Yeah. Yeah. Any questions? Okay, one thing I should admit, this proof is very abstract. It's very, very abstract, and it's kind of very slick, and a lot of details are hidden there. You have to patiently sit through and justify every step. There is a purely computational proof, which is a pain, because then that means you have to compute determinants of huge matrices. You just write down, because you have to compute some differential choosing coordinates. It is possible to do it that way, but that's very uninspired also. But I mean, this is a very slick proof, but that is abstract. We use some technology which is a little more like that standard. But otherwise, that's okay. Yeah, so, okay. Now, what we want to do now is to relate this constant Cn to, of course, I mean, this is the van der Moon determinant. Van der Moon determinant of lambda squared. So this is van der Moon determinant of lambda squared. It's here, use here. Now to relate Cn to volumes of unitary group, UN. Okay, first of all, what do we mean by volume of unitary group? With respect to what measure we are talking about? Well, I mean, we have a metric on this Lie algebra of the unitary group. So let's see. So let's look at Lie of UN, right? If you look at Lie of UN, this is the just I times n by n Hermitian matrices, right? So these are the skew Hermitian matrices. Skew Hermitian. Okay, but there is a metric here on the this is the tangent space of UN and identity, right? There's a metric here, and the metric is just this thing which is trace of S squared, right? The metric of two matrices here, A and B, is equal to trace of A star. This is the metric induced from Zn to big space. This is exactly, I mean, there's also exactly similar metric induced on Hn without I. But these are these two wings, they decompose n by n complex matrices to two subspaces of dimension n squared each. Right? So metric on, okay. So induced from Cn. Oh, what is induced from Zn? You see, this Zn, we can write it as, again, Hn, direct sum I, Hn. So this metric here that we are using is the negative of the killing metric. You can just show that this is equal to negative of the killing metric. It doesn't matter what killing metric is. on this sort of semi-simple Lie groups, that's okay, or Lie algebras. In this case, Lie algebra. But the point is the following. So we have a metric on the tangent space of this Lie group at identity. And this metric obviously is unitary invariant. If you multiply A, you see, what I mean is the following: trace of, the inner product of U A, U star, and U B, U star is equal to inner product of A and B. You can check this, right? Because you put it here, you just can't, by trace property, they cancel, and unitary property, everything they cancel, they get. Okay, and so then you can use this metric to translate it to everywhere on the Lie group. Then you get a unitary invariant metric on the Lie group, which is UN. And it is with respect to this volume form, coming from this metric, that we want to compute the volume of UN. Okay. So, and this is exactly embedded in this formula. So if in this formula I just put F equal to identity, then I'm reduced to the volume of the unitary group. So let me write it. So which one constant function. Then we can compute integrals. So let's compute this. We put 1 over 2 pi m squared over 2 integral over hn exponential of -1/2 raised of h2 d tilde of h. Okay, I know that this is just the mu of h. If you want the mu tilde of h, maybe. And this integral is 1 because I have normalized everything. I'm integrating constant function 1 here. So this part is 1. And this is a constant. But while integration formula tells me that I can write it as an integral over now, over this one, over Rn. So let's see what is that. So this is equal to 1 over 2 pi the power n squared over 2. Here we get volume of UN. Now, you have to be careful. Why we get volume of UN? Why do we get volume of UN? Because this function is constant, so the U part gives us the volume of UN. So I believe this should be okay. Although now I'm a bit hesitant to say it's okay. Okay, let's accept this, and then maybe I justify it by a different method. But then the formula, that formula, if f of lambda is equal to 1, so this becomes integral of times here times integral of product over Rn. Oh yeah, there is something else I did not describe, but I will do it now. I less than j lambda I minus lambda j squared exponential of -1/2 sigma lambda k squared, k from 1 to n. Yeah, times product of d lambda k, k from 1 to n. Yeah. Okay. So the idea now is that if we can compute this integral, which is just integral of van der Waals determinant with respect to the Gaussian measure on our end, the standard Gaussian determinant, then we can compute volume of the unity. So, but computing this integral is very hard. There's no easy way to compute this integral except developing some fancy techniques that we'll do next. But that's the strategy. One thing I did not describe. You see, in the formula that I wrote, I reduced everything to an integration over the n cross u n bar. First of all, this Tn, the Weyl chamber is lambda 1 less than lambda 2 less than lambda n. But you see, this function that we get is actually symmetric function. So I can integrate over the whole Rn and then divide by n factorial. Because the whole Rn is the union of n factorial of these Weyl chambers up to sets of measures 0, where lambda I is equal to lambda j for two adjacent ones. Not a problem. So if you write this integral, you can say that this integral is n factorial times integration over the Weyl chain. So that's that part. The second thing is that we are over, honestly, un bar, but my calculation was over un. But the relation between the two is very easy because un bar is un over Tn. That's the quotient space. And the volume of this in respect to the induced metric is just volume of the circles to the power n, which is 2 pi to the power n. I mean, volume of the circle, I mean perimeter of the circle. The circle has only one volume, that's the length. It's a one-dimensional manifold, this volume is length. So we have got only this much. So we just we integrate over this and divide by this guy. And that justify part of this calculation. So, okay, I mean, yeah, we have to get into something very specific in order to actually, yeah. So I don't want to continue this now because, I mean, the explanations I think are more or less complete. Well, yeah. I would say not perfect yet, but it's okay. Right. So now, what yeah. So what does this formula mean really? This Weyl integration formula means. So let me discuss a little bit. Immediate consequence of this. Okay, so something interesting and that strange happens with GUE. See, so imagine you have a matrix in GUE, right? So H equal to Hij, right? So we know that it's a probability space, right? GUE. I mean, there's a probability measure right here, which is d mu of h, right? Or d mu tilde of h by some scaling, doesn't matter. But probability is the same anyhow. So this is equal to whatever it is. So now, so it's a probability space, okay? Now, if you look at these variables hij from hn, you see for I less than equal to j, these are all independent random variables. They're all independent random variables. Independent Gaussian complex valued random variable. So we say the entries of a GUE matrix, except for symmetry, which of course the one on the top, on above diagonal and below diagonal, they cannot be independent because they're the same or conjugate of each other. But otherwise, they are independent of each other. So all entries are independent. So can you tell me why the entries are independent? So the question is why the entries which are hij are less than equal to j are independent. For example, why h11 and h22 are independent of each other. As random variables defined on this probability space. So what we have to do, we have to look at the probability distribution function. And if the probability distribution functions can be written as a product of this variable, then it means that they are independent, right? So let's look at the probability distribution function. I mean, this d mu of h is 1 over z exponential of minus trace of h squared dvh, right? So let's see what are these variables. This is equal to 1 over z exponential of minus sum I and j from 1 to n. I mean hij, hji, right? So what is that? That's equal to 1 over z exponential of minus sum hii squared, if I is equal to j, and the rest are and then negative twice. Okay, I have to put minus 1/2 here. So this is minus 1/2. And then minus 1/2 times twice sum hij, and then hji is hij squared, right? I mean hij bar, because hji is hij bar. So what are they? I mean, first of all, I mean, it's a property of exponential that you can write this as product of exponential of minus 1/2 hii squared. These are real variables, I from 1 to n. So obviously this part is independent. The rest is also has a product structure. They decompose. So we get the product of exponential of minus absolute value of hij squared. I mean I less than j. So it completely disentangles the measure, disentangles into product measures. So they are independent. So if you sample a GUE matrix using any program, your computer, you notice that the entries are going to be independent statistically. But now if you look at eigenvalues for these things, So what about the eigenvalues? I mean, if you look at eigenvalues, we've got lambda 1, lambda 2, lambda n, right? We have n eigenvalues. Imagine we have ordered them. They go from Hn also to C, I mean to R in this case, actually. So we have got these random variables. Now I ask the question, are they independent? Are these random variables independent of each other? So it's kind of funny because these entries of the matrix are independent of each other. But we're asking now the question, are the eigenvalues of these independent matrices are independent of each other? They are not. And this is shown by this formula. This formula does not decompose as product of measures. This you cannot write it as product because there's a mixing. They fill each other, eigenvalues. And in fact, eigenvalues repel each other. So let me tell you. So now this is the idea of eigenvalue repulsion. This is very important. So first of all, this distribution is the joint probability distribution of eigenvalues, what we have. JPDF, joint probability distribution function of lambda 1, lambda 2, lambda n. So what is that? This is basically probability of finding a matrix whose eigenvalue is in the vicinity of this point. This is JPDF. Probability of all those H such that lambda 1H, lambda NH belong to this box. So let me put this box as B, lambda 1, lambda 2, lambda n, epsilon. So in this Weyl chamber, we just pick one point lambda 1, lambda 2, lambda n, and we put a epsilon box around it. And we ask, what is the probability of finding a matrix whose eigenvalues are here? This is a very legit question. And this probability is exactly given by this quantity. So this is equal to integral over this box, lambda epsilon of that function, product of the Vandermonde matrix, product of lambda I minus lambda j squared, d mu lambda I. I mean, I have to normalize this by some suitable normalization to get product, but that's okay. And now you see that actually, if lambda I and if epsilon is very small, then this quantity becomes zero actually. Because if lambda I is equal to lambda j, it becomes zero. So eigenvalues do not like each other. This is called eigenvalue repulsion, and is a very important aspect of random matrix theory. So this is eigenvalue repulsion. So yeah, so basically you can write, I mean, alternatively, you can write this term as exponential of log of absolute value of sum lambda I minus lambda j squared. You can write this in this form, right? When you write it like this form, and you notice that, okay, so there is this Gaussian contribution, and then there's an interaction part. So the eigenvalue eigenvalues are not free. The interaction between them is governed by some Gaussian part, which is the free part, but then there is this potential. And this is actually called Coulomb potential. Coulomb potential. And do you know the reason it's called Coulomb potential? Because in 2 dimensions, the Coulomb force is logarithmic. The potential for the Coulomb force in 2 dimensions. In 3 dimensions is 1 over r, but the Green function for the Laplacian in 2 dimensions is log of the distance. So it's Coulombic, and that's called Coulomb potential, and that gave rise to a lot of nice intuition, the way thinking about this random matrices. So we'll also look at some of those. Okay. I think now I want to stop for 10 minutes and then we'll come back and continue because we are not done yet. Okay. Any questions? So we come back in roughly 10 minutes. I just put pause. Resume. Okay, now we are resuming. Yeah, so the question in the chat was what happens in the supersymmetric case for Grassmannian's variables? I'm not sure because, yeah, the whole integral is finite dimensional in that case. I mean, we are integrating. If it is just, yeah, but if you are in supersymmetric, so you're mixing both variables, symmetric and skew symmetric, then something interesting could happen. Short answer is I don't know the answer really right now. Yeah, it's funny. Actually, one of my papers, I was supposed to be working on that, so I've forgotten. But yeah, that's a very good question. Let me know if you find an answer. Yeah, I will think about it. Sure. For sure.
I think there's also like a square root in the Pfaffian, so it doesn't quite cancel. But yeah, I'll read up some more on on that.
Yeah, no, absolutely. Yeah, I mean there is this theory of what's it called? Yeah, random variables for supersymmetric matrices and this thing. So, and most probably you get more interesting algebraic results in that case. Yeah, but yeah, I don't know. Okay, so we can now continue. So with very nice applications to start with. So this is called method of orthogonal polynomials. And so it's a very general idea for MT, random matrix theory, which we need. I mean, eventually we will use this, maybe even today, to compute volumes of unitary groups. And also we will prove this Harari-Zagiev theorem. Harari-Zagiev. Not the one about cohomology of moduli spaces, but which we'll do later. But it's about this counting how many surfaces of genus G you obtain if you glue a 2M gun, for example. These epsilon GM functions will get some explicit formulas for those. And Harari-Zagiev. Okay. So what is it? So yeah. So let me introduce Hermite polynomials. Actually, there's no E. Hermite polynomials. Is there an E or without? There is a yeah. That's why, because some English-speaking people call it Hermite or something. But it's Hermite. Yeah, for its French name, great mathematician, 19th century. with polynomials. So H0 of x, H1 of x, H2 of x, etc. So there is a formula for them. So I just write the formula, totally uninspired right now, but I will tell you where they come from. Hn of x is equal to -1 to the n exponential of x2 over 2 dn dxn exponential of minus x2 over 2. You see, this is a polynomial. It looks like there's exponential term, but they cancel. Positive, negative, only a polynomial remains. So H0, you can easily compute H0 of x is equal to 1, H1 of x is equal to x, H2 of x is equal to x2 minus 1, H3 of x is equal to x3 minus 3x, and H4 of x is x4 minus 6x2 plus 3. So, yeah, so they have the following properties that Hn is a monic. So it's normalized in such a way that it's monic polynomial of degree n. It's monic of degree n polynomial. Yeah, that's one property. And Hn form an orthonormal basis, actually orthogonal, not orthonormal. That's important. Hn, and from 0 up to infinity is an orthogonal basis. For yeah, for L2 of R with respect to normalized Gaussian measure. For L2 of R with respect to this normalized Gaussian measure, which is 1 over root pi exponential of minus 1/2 x squared d lambda of dx. Not with respect to the Lebesgue measure, because with respect to Lebesgue measure, they are divergent. The integrals are divergent. So basically, it means what this means. It means that integral over R Hnx, and I don't have to conjugate because it's a real polynomial, so that's fine. Exponential of minus 1/2 x squared dx 1 over root 2 pi. Yeah, it's equal to 0 if n is different from n. And we know actually the value of this when n is equal to n, essentially. So let me put the value. The second part is that Hn to satisfy these recursions is x h n minus 1 minus h n minus 1 prime. This is the derivative. And that's the important one. So Hn and Hn, this is the inner product, is equal to n times h n minus 1 h n minus 1. So if you do the recursion, you notice that the length squared of Hn is essentially n factorial, if you can. You continue. Okay, I mean, it's really a Hilbert basis. It's not just the orthogonal. They span in L2 sense, all square integrable functions with respect to this. Okay, so one question is where they come from. You may encounter them in many places. One of them is quantum mechanics. These are the eigenstates of quantum harmonic oscillators, basically. So there's a strong tie to quantum mechanics. I just say Hn of x, and from 0 to infinity, these are eigenstates of quantum harmonic oscillator. Of the solutions of Schrödinger's equation for quantum harmonic oscillator. The quantum harmonic oscillator is the following operator on L2 of R, H, minus 1/2. Now, you have to put different normalizations. I'm assuming mass is equal to 1, Planck's constant is equal to 1, and so on. So this is 1/2 d2 dx2 plus 1/2 x squared. This is the, this gives you a Hooke's law in the classical case, the quantum case. I mean, people are also putting x hat here. Maybe they want to emphasize it's an operator, it's not just a way. That's okay. The multiplication operator by x by this. So this has eigenvalues essentially n plus, so yeah, it's unfortunate. H of Hn is equal to n plus 1/2 Hn. So these are essentially eigenvalues n plus 1/2. That's where actually Planck could not see this 1/2 in his paper. They introduced quantum harmonic oscillators in an ad hoc way. He assumed that the ground state is 0. It's not 0. This is a big difference between quantum and classic. In the classic, a spring can be cannot move. Maybe it just stays silent, is in equilibrium and doesn't move. Its energy is 0. But in this in the quantum case, the energy is never 0. Even in the equilibrium, quantum harmonic oscillator has energy 1/2. I mean, okay. So anyhow, we can derive this using rigorous analysis and all these things, but that's not the point. We want to use them. So, okay. So we just use these things. Another warning is that, yeah, Wikipedia says actually in probability theory, they use, I believe, a different normalization or vice versa. There is a normalization where you get coefficients here, and then you have orthonormal basis, not n factorial, but it's clear what to do. Just divide by 4. Okay, so now what we want to do with this is following basically amazing thing. So we can express van der Waals determinant so let's look at this term, product of lambda I minus lambda j, I bigger than j, for example, doesn't matter, which is this one, is 1, and then, yeah, lambda 1, lambda 2, lambda n, and then lambda 1 to be n minus 1, lambda 2 to be n minus 1, lambda n to the power n minus 1. So the claim is that this van der Waals determinant is equal to actually H0 of lambda 1 H0 of lambda 2, H0 of lambda n here. And then the last one, we put Hn minus 1 of lambda 1, Hn minus 2 of lambda 2, and Hn minus 1. Oh, Hn, not minus 2, Hn minus 1, sorry. Hn minus 1 of lambda. Yeah. Okay. So it looks like that we had something which was nice, like van der Waals determinant. We made it immensely more complicated by replacing these values, these eigenvalues, by values of these polynomials in that. So, proof, how to prove this? Proof is actually not difficult because you should have to observe that. So let's see, we can prove this. I mean, first of all, this H0 is a constant function. In the first row, exactly the same thing appears. Now here, in the second row, I have H1 of lambda 1, H1 of lambda 2, H1 of lambda n, right? If you look at H1, it's like X, okay? So the second row is also the same, it's reproducing the same thing. So no argument needed. Now let's look at the third row, which is H2 of lambda 1. And then H2 of lambda 2. And then H2 of lambda. Okay, there is this term x squared, which is producing exactly the third term here. But then there is minus 1. Minus 1, minus 1, minus 1. But this minus 1, minus 1, minus 1 is determinant with the first row is 0. Because two rows are the same. So you just delete that and then you get this. And now as you go down the row, in the next row, we have this 3 lambda 1 here. This also cancels with the second row. So it does not contribute. So basically, you see that all these nuisance here do not contribute. So, and in fact, I did not use all of properties of Hermite polynomials. I just used the fact that Hn is a monic polynomial of degree n. That's all. We did not use orthogonality yet. We did not use anything special about the structure of coefficients now. Just monic polynomial of degree n always works. So that's the thing. Now we are going to prove this proposition, which actually calculates that integral that we wanted to calculate in terms of so here's the proposition. Yeah, so integral over Rn, a product of I less than j and I minus j squared mu lambda 1 and mu, and then I mean this Gaussians. These are Gaussians, and this is this van der Waals determinant. This is actually equal to n factorial, the inner product of H0 times the inner product of H1 H1, and then times inner product of Hn minus 1. We've got that thing now. Okay. So to prove, I mean, okay, so here we have square here. You want to compute the square. This is the square. This is the square, yeah. Okay. And so when you expand and so let me just write this statement. And using orthogonality of Hermite polynomials, and expanding the determinant. This determinant, I mean, Hermite ones, not these ones. The Hermite ones, which is the same. We get some terms of the following forms. We see that only monomials of the form H0 squared lambda sigma 1 H1 squared lambda sigma 2 and the sum over of permutations H n minus 1 squared lambda sigma n contribute. Okay. So yeah, because you see, I mean, when you expand here, if you have a term like H1 lambda 1, H2 lambda 2, these things become orthogonal to each other, they cancel, it's zero. So only it's coincidence that two things are the same, they appear and remain, I mean. So we get this result. Because there are n factorial sigmas, and each of them give you the same thing, so they just sum over distance. So yeah, so what happens is that they can compute actually this strange integral. I honestly don't know any other way of computing this, but maybe there are. I would be surprised, but this orthogonal problem is very standard. So yeah. But we know these values. So as a result, so on Wednesday, what day is today? This is Wednesday. Okay, so then next week we'll just continue and compute the volume of the unitary group and prove this Arezaghi theorem for. There's a very nice formula for the volume of the unitary. Okay, so I think we are good now. Just stop.